the heart of the entire semester. Okay, the whole point of this course is to understand what the number means. Okay, what a function is, and be able to tell properties about a function, analyze it, graph it, many things. Now, of course, we're not going to be able to graph any function that comes our way. That's why you need to study calculus. Okay, one of the options in calculus 1 is to be able to take any function and sketch its graph. Okay, but here we're going to study some special ones that we'll be able to do without having to use any of the advanced techniques. Not advanced, but more fancy techniques that are done in calculus. Okay, but this is you could say this is one of the most important notions in mathematics. Okay, the notion of a function. Okay, but before I explain what a function is, let's talk about relations. So, anybody, do you know what relation is? Those are operations on a set. So it's very easy. I mean, it's just that maybe you don't know it by this name, but a relation is just a set of ordered pairs. Okay, that's all it is. It's just when you have a bunch of ordered pairs together. So you could have many type of relations, like I don't know, a name. So a person, comma is age, and then you consider I don't know in this room the collection of all names together with their ages, right? So that would be a relation. Okay, it's just a set of ordered pairs. In our case, we're gonna have a set of numbers of ordered pairs of numbers x comma y. Okay, that's what a relation will be. So let me define this. And the thing is that every function is a relation, but not the other way around. There are relations that are not functions. Okay, so we first are going to understand what a relation is, and then we talk about functions. Okay, so definition. What's a relation? A relation is just a set of ordered pairs. Okay, a relation is a set of ordered pairs. Okay, so typically we refer to the ordered pairs as x comma y. Another pair, we look at it, if we're talking about numbers as x comma y, the reason why I'm writing this is to make it more easy to define the next two notions, because then given a relation, there are two sets that we can define. One is called the domain, another one is called the range. What's the domain of a relation? You just take all the other pairs, look at the first guy, and then you collect all of those elements, that's the domain. What's a range? You look at the other pairs, look at the second guy, collect all of those elements together, that's a range. Okay? So, a relation is a set of ordered pairs. Typically, we refer to these ordered pairs as x comma y. And then the domain of a relation is the collection of first elements in each ordered pair. Okay, so in other words, all the x's, okay, so all the x, and then what's the range? The range of a relation, it's the same thing, it's just that you look at the second line, okay, the second element in each of the pair. So the range of a relation is a collection of the second element in each ordered pair. Okay, so in other words, all the y's. So what's important is that, the property of a range is that when you have an element in the range, so when you have a y, what you're saying is there is an x that's related to that y. Okay? So this is what a relation is for us. It's just a collection of ordered pairs. In mathematics, typically when we're dealing with relations, we say x comma y, or we say x is related to y. Okay? Since we're going to be talking about functions, we're going to denote these ordered pairs in another form pretty soon. Okay, but right now this is what we have. So let me give you an example. So actually, let me define something else. There is a notion of the graph of a relation. So what do we mean by the graph of a relation? Now, not every relation has a graph unless you give a meaning to how to, what x and y are. Now, in our cases, most of the time, these guys are going to be numbers. And when these are numbers, we know how to plot these numbers, okay? So when there will be a graph, and what's a graph is just the collection of all of these points plotted on an xy plane, okay? So the graph of a relation is the collection of all xy ordered pairs in the relation plotted on the xy plane. Okay, so every relation, if your ordered pairs x and y are numbers, then you can talk about the graph of this relation, which is just plot all of these points. Okay, and then that's going to give you the graph. Let me give you some examples, and I'm going to give you some relations, and then I want you to tell me the domain and the range of the relation. Okay, so let's see. First one, and also graph it. So let's say find the domain and range. And let's see, let me first do, let's say our relation R is given by 1, 2, 0, 1, 1, 3, negative 1, 4. Okay, so this is a relation. It's just a collection of ordered pairs. So in this case, we have 4 ordered pairs. Okay, so let's see, who can tell me what's the domain of this? What is the domain of this relation? Yes?
1, 0, negative 1.
Very good. 1, 0, negative 1. Notice that here 1 appears twice. That's okay, but there's no need to repeat it here. Okay? So remember, domain is just pick the first guy from each other pair. That's all it is. And how about the range? What's the range of this relation?
1, 2, 3, 4.
So let's see, I'm gonna go in order. So 2, 1, 3, and 4. Remember, a set is a collection of elements. The order inside doesn't matter. So it doesn't matter. Very good. So just go and look at the second element in each other pair. Any questions about this? What domain and range is? Now, if you want to see a picture of this relation, I mean, it's not too fancy, but you could sketch a graph of this relation. Which in this case, you just plot these points. So that's 1, 2. So here is one element in the relation, and 0, 1. Here is another element in the relation, then 1, 3. Here is another element in the relation, and then negative 1, 4. Okay, so this right here will be the graph of this particular relation. So in other words, when the relation has a finite collection of ordered pairs, this is how it's going to look, like a bunch of dots. Okay, that's all it is. You got finitely many. Of course, we're interested in studying relations that have infinitely many ordered pairs. Okay, and then when you have infinitely many ordered pairs, the graph here is going to look a little bit more interesting. Okay, we obtain a curve, which is what we are used to see when we think about graphs. All right, so then let's quickly go there. So as another example, the relation may be explicitly given to you like this, as a set of ordered pairs, or it may be implicitly given to you via an equation, perhaps. Okay, so for example, how about x minus 3 squared plus y squared equals 9? And what do I mean by this? What do I mean when I write this down? Why can we think of this as a relation? Well, we think of this as a relation because what I'm saying here is that the ordered pairs in the relation are those x, y. So when you plug it in here, they satisfy this equation. Okay. So if you want a more fancy way, would be to write the set-builder notation. So the relation is the order pairs x comma y such that when you plug them in this equation, they satisfy us. In other words, x minus 3 squared plus y squared, they have to give you 9. Okay? So this is a relation. Okay, it's just a way of describing order pairs, and as you know, this is not an empty relation. In fact, what is this? If you want to look at a picture of this relation, how does it look like? Yes?
Circle.
What is it? What circle is this?
A circle. You want me to give you
You need to give me center and radius. When I ask you what circle, the important data is center and radius.
Circle with center 3, 0, and range 3.
And radius 3.
Radius 3.
Okay, good. So in other words, what are we talking about? What are the order pairs? Well, so what is it? 3, 0. So let's say 3 is here, that's the center. Then we go here, 3, and 6, 3, -3. So we're talking about all of these points, okay? All the points on this circle, these are the elements in the relation, okay? So my x comma y's are points in here. These are the points that we're talking about. Now the thing is that there are infinitely many points here, right? So we cannot just start writing down one by one. So what do? Well, we write down the equations satisfied by those points. Do you understand this? These are relations. Now I want you to tell me what's the domain and what is the range. So domain, range. Right, so what's the domain for this relation? So it's right here, it's a 6. Yes?
Isn't it 0 through 6?
Very good. So, in other words, in this case now, it's very helpful to look at the picture, okay? The graph actually is the one that will tell you what the domain is. If you look at it from this point of view, it's more complicated to figure it out, okay? So remember, the domain is all the x's. From all the points here, you just want to collect all the x's. Well, every element between, for every x between 0 and 6, no matter what x you give me, there will be a point corresponding to it on the circle. In fact, there are 2 points with the section of 0 and 6. Do you understand this? And actually, if you get outside this range, less than 0 or bigger than 6, there is no point on the circle, so we don't need to care about those. Do you understand this? So every point here has x between 0 and 6, and the other way around as well. Any x between 0 and 6 will have a point on this relation. So the domain is x between 0 and 6 included. Typically we write this, but since it's understood that typically we mean x is the domain, then we also write interval notation. So in interval notation, that will be this. The thing about this is that you need to understand that we're talking about x and not about y, okay? If you want to specify that we're talking about x, then you write this one, the inequality form, okay? Good. All right, so then similarly, how do we figure out the range? What's the range of this relation? Let's see, somebody on this side, what's the range of this relation? Yes?
X or Y between 3 and -3 included.
Very good. In other words, remember, for domain, it was the x-axis. So you can think of the shadow of the circle, the shadow of the curve onto the x-axis. That's the domain. Now, for the range, it's the same idea, but you have to look at the y-axis because that's the one that has to do with the second elements, right? The second elements in the order pairs, those are given by the y. So if you want to look at the range, you should be looking at the shadow of the circle onto the y-axis. And just doing the same analysis, anything between -3 and 3. So pick a number between -3 and 3. There will be 2 points in the circle corresponding to that number. And also any point on the circle has y between -3 and 3, right? Below 3, there is nothing to look at. Above 3, there is nothing to look at. So that's what we get. All right, so the range is y between -3 and 3. And once again, here we are stressing the fact that it's a variable y, but you could also write it in interval notation like this. But now, if you write this has to be accompanied by the word range. Because otherwise, I don't know, are you talking about X or are you talking about Y? Okay? All right, questions? Yes?
When we get like the test for this, will we have to write it in the editable notation or?
It will tell you, or if it's multiple choice, then you will see the choices, whether one or the other. Okay? All right, any questions? Okay, so let me give you one for you to try. That was number 2. Why don't you try this one? Number 3. X plus 4 squared plus y minus 1 squared equals 4. So determine the domain and the range. Give you 2 minutes. Okay, so what type of relations do we have in number 3? What is this?
It's a circle.
Is a circle, or what circle?
Center at -4, 1, and the radius 2.
Okay, so let's write here. So this is a circle, and the center is -4, 1, and then the radius is 2. Good. So what's the domain of this circle?
The interval bracket -6, -2.
-6, -2. Very good. So in other words, just start at the center. If you want to know the domain, just add 2 to -4 and subtract 2 to -4, so you can get the 2 points, the 2 horizontal points. Do you understand what I'm saying? So there's no need to actually draw the full circle. You have everything here. Like in this picture, you just stand here and then you do +3, -3, and then you get the whole. Okay, good. And then what about the range?
Bracket -1, 3.
So -1, 3. Very good. In other words, you are at y + 1, you do +2 to get the top, -2 to get the bottom. That's it. Questions? All right, so then let's do something similar, but now, let's see, that was 3, so let's call this one number 4. Let's call this one number 5. So instead of giving you an equation, so again, a relation may be presented to you via a set of ordered pairs, like what we did in sample number 1, or it may be presented to you via an equation, and you need to understand that the relation is the solution to this equation, okay? The ordered pairs satisfy this equation. Or it may be presented to you already as a picture, like this graph, okay? There's no equation, I'm not giving you any equation here. However, by showing you this graph, our relation is a set of ordered pairs that lie on this graph. In other words, points here. on this picture, they are a relation. Like for example, the point 2,5 would be an element in our relation. Do you understand this? Okay, so this is a relation, therefore it has a domain and it has a range. So domain, range. So who can tell me what's the domain for this relation? Yes?
Parentheses, -1, and then, so for the bracket.
Very good. So remember, domain, just look at the shadow of this picture onto the x-axis. So it begins here at -1. Let me stress this. It begins at -1 and then it finishes here at x equals 4. Does everybody see this? So that's your domain, -1 to 4. Good. And notice that we use parentheses. Why do we use parentheses? There's an open circle. So what are we saying in this picture? What do we mean by this open circle?
It doesn't include that.
It means that this is not a point on our graph. Okay, this point right here does not belong to the relation. This closed circle means that this point is part of the relation. Okay, that's why we put a bracket around 4. Good. How about the range for this? -1 comma, let's see, 1, 2, 3, 4. Yes. And then we put brackets around. You okay with this? All right, perfect. So once again, just look at the shadow of your graph onto the y-axis. Okay. So domain, you have to focus on the x-axis. Range, focus on the y-axis. All right. Any questions regarding this one? Okay. About number 5. Let's write domain, then range. So this little arrow just means that the graph keeps going up non-stop. Okay. When I want the graph to stop somewhere, and you will see like an actual circle showing up, like in this case. Like we put a closed circle or something like that. Typically, I'm not going to be, when I actually draw these things, I'm not going to be putting the arrows, but you need to understand that even if there is no arrow, if I did not do a closed circle, it just means it keeps going. Okay? So this graph keeps going up both ways. All right. So what's the domain? Yes?
Negative, parentheses, negative, infinity, positive.
Very good. Does everybody understand this? So remember, this keeps going up both ways, but it's going up and opening at the same time. Okay? So if you go all the way to the left, this part right here, this branch is going to cover the left part of the x-axis, and as this keeps going up, it keeps opening also towards the right, so it will cover the right part of the x-axis. So the entire x-axis gets covered. So the domain is all real numbers. Okay? Negative infinity, positive infinity. Good. How about the range? What's the range? Okay, let's see. 3 is part of the range because this point right here, y equals 3. But is that just okay? Exactly. So notice that if you look at this picture, what is the shadow of this graph when you project it onto the y-axis? Right? Anything above 3 would be will have a point on this graph. You understand this? Remember, this keeps going up both ways. So there's nothing going on down here. So the y's down here, they're not good, but starting at 3, everything else is taken care of by this graph. Okay, so that would be 3 with bracket, comma, infinity. Or y greater than or equal than 3, if you want to write it with inequality. Okay, questions? Do you understand this? Okay, good. So now that we have a little understanding of what relations are, again, our main focus on our relations are actually functions. So let me define what a function is. So basically, a function is a relation, but it's a special relation. For example, we don't want this kind of stuff. Okay? So you see, in this relation, we have a set of ordered pairs, but it turns out that there are 2 ordered pairs here that have the same x value. You see? So for example, if I tell you here, if I ask you who is related to 1, what value is related to 1, then you have to give me 2 answers, right? Because according to this relation, 1 is related to 2, but also 1 is related to 3, right? Now, a function does not like this kind of stuff. We want to say that each element in the domain is related to only one element in the range. Like, for example, 0 is only related to 1. That's it. Not related to anybody else. And same thing with -1. So those two guys are okay, but 1 is not good here. It's related to two different elements. You understand this? So we want to avoid that kind of situation. Circles also are not good. Like, for example, let's look at the x in the center. For example, 3, right? Here, if you pick x equals 3, it's going to be related to two guys. It's related to positive 3, but it's also related to negative 3. That's not good. Okay? So we want to avoid this kind of stuff. And when we eliminate that condition, so when we impose the condition, let's just say that every x is related to only one y, we obtain what we call a function. Okay? So definition. Function. So a function is a relation. Remember, every function is a relation, but it's not true that every relation is a function. Okay? So a function is a relation such that for every x, there is exactly one y. It is exactly one y related to. Okay? In other words, every element in the domain is related to only one element in the range. So every element in the domain is related to only one element in the range. Okay, so an element in the domain cannot have two different. So the elements in the range are called the images of the elements in the domain. So what we're saying here is that each element in the domain can only have one image. Okay, cannot have two or more images. Okay, so another word for range is image. So in math, typically that's a more fancy word. So let me put it here. So range in the definition. Range, and sometimes if you read other texts, you may also see the word image. Okay, it means the same. Image and range is the same. All right. So for example, let's go back and let's try to determine from the above relations which one is a function and which one is not a function. So I guess I'm gonna call this one relation 1. Let's call this one relation 2. This one corresponds to relation 3. This picture here will be relation 4. And this picture here will be relation 5. Okay? The 5 relations that we have here. So example, determine whether the above relations are functions or not. If it is not, justify. In other words, you need to tell me why you're telling me that it's not a function. Okay? All right, so let's see. R1. Is R1 a function? Why? Because 1 has 2 images. Very good. So this is not a function, so R1 is not a function. And the reason is because 1 is related to both. So what were they? 2 and 3. To both 2 and 3. And that's not good. Okay? All right. How about R2? Is R2 a function? Why? Say that again. What do you mean all? Well, this point doesn't have 3 correct, right? And for example, this point has 6 correct. But let's see, can you tell me? Remember, you only need to give me 2 points that share 3. That's all you need to give me. So can you see 2 points that share 3? What are they? And 3,3. Good. So this is not a function. I mean, you can give me whatever you want except these 2 points. These 2 points are the only ones that are okay. Yes? But the others are a problem now. If you don't pick these 2, then you have to do some computations. Okay? So the easy ones are these 2. So you can say it's not a function because, for example, 3 is related to both 3 and -3. It doesn't make difference. Okay? So 3 has 2 events. So 3 and -3. So not a function because let me write now a little bit different because 3,3 and 3, -3 are elements of R2. Okay? So this is a way of saying that 3 is related to both 3 and -3. Okay? In other words, if you think of it as ordered pairs, you don't want repetition in the first spot. Okay? If an element shows up in the first spot, then it cannot appear in the first spot again for the other ordered pairs. If it appears, it's no longer a function. Okay, good. How about R3? How about R3? Is this a function? So why is it not? So
in a circle, the extra piece because there's a point above it and a point below it. That's in a circle.
okay, so give me 2 complete points.
For that one, it could be -4, 3 and -4, -2.
-1. So use the range. Remember those points, the top one and the bottom one, which are the one corresponding to the center, are the points on our range. Yes? Remember the y here is 1, so you go 2 units down, that's a -1. So -4 is related to both -1 and 3. So that's not good, right? So not a function because -4 is related to, what was it? -1 and 3?
Yeah.
-1 and 3. Is related to -1 and 3. Okay. Now how about R4? How about R4? It is a function.
Yes,
Why?
because each x only has one y.
Exactly. You won't be. There is no x here. You can. I mean, looking at the picture, you realize that there is no x that will give you 2 or more y's. Do you understand this? Every point that you pick on this picture only has, for each x, there is only one corresponding y attached to it. There is no multiple y's. We're going to pretty soon give it a name to how to quickly identify whether a graph corresponds to a function or not. Basically, what I'm talking about is what we call the vertical line test. Okay? So when you have a picture, that picture represents a function. If no matter what vertical line you draw, it crosses the graph in at most 1 point. Okay? So if you could draw a vertical line that will cross the graph at 2 or more points, that's it. It's no longer a function. Okay? Like for example, in this circle, I can draw a line like this that will cross at 2 points. So that's it. It's no longer a function. Okay? In this little example here, we could draw the line x equal 1, which is a vertical line, and then it's going to go to these 2 points, no longer a function. Okay? Basically, when you draw a vertical line, what you're doing is you're fixing an x value, and then you're trying to see how many y's that x has by looking at points of intersection. Okay? That's what you do when you draw the vertical line. So in this case, no matter what vertical line you draw, it will only either cut at one point or not at all. If you do it over here, it's not gonna touch it, right? But that's okay, doesn't matter. So yes, it's a function. It is a function. And how about relation number 5? Is this a function? Yes, it is a function. Once again, no matter what vertical line you draw, it will only cross at one point. Yes? There is no x that has multiple y's. So yes, it is a function. Questions about this? Now, you know, the way that we actually decided whether these things were functions or not, it was, we kind of rely on the picture in a sense. And here we kind of rely on the fact that even though we didn't actually have the picture, we know this is a circle. And so we're able to come up with this pretty quickly. But what if you have an equation? Are you really going to graph the equation to then try to figure out whether this is a function or not? So the question is, how do you determine this algebraically? How can you tell algebraically whether a given equation defines a function or not? I'm talking about equations because if you're given a set of ordered pairs, you can just look at it and see there's no repetition or whatever. So that's easy. If you're given a picture, it's also easy. We have the vertical line test. What if you're just given an equation? Okay. So let's do a couple of examples with that, just to explore this idea. Or let me write down the vertical line test. So vertical line test, and then we do the algebra part. Basically, I'll tell you when it's not a function. A relation is not a function if you can draw a vertical line that crosses the graph at 2 or more points. Okay? So a relation is not a function okay, what's going on? So a relation is not a function if you could draw a vertical line that crosses the graph of the relation at 2 or more points. At least 2 points, then that's it, it's not a function. Now, if you cannot do this, in other words, if every vertical line that you draw only crosses at most once, then yes, you have a function. So it's a very nice and easy test to use, but this is helpful when you have the picture, when you have the graph in front of you, but what if you don't? Okay? So, question is, okay, this is good, but what if we don't have the graph? And typically this is the case. Typically we don't have the graph, right? What if we don't have the graph? So for example, let's assume for a second that we don't know. I mean, here we know the answer, right? So what's the answer? Is it a function or not? We know the answer is no, right? But let's say that you didn't know how this looked like, that you didn't know that this was a circle. How could we determine that algebraically? Well, in this case, the equation is easy enough that you can start thinking about it, and then, just if you can find an x that has multiple y's, satisfying this, then you're done. But if the equation is more complicated, then guessing does not become a very straightforward thing to do. So typically what we do is we solve for y. And then as you solve, what's going to happen is that if you get y equals some formula that only has x in it, and then, that means that for each x that you put, you evaluate this part, you get a number, so each x has a y. But if, as you solve, you have to do plus or minus. What's going on is that when you have an x, then there will be two different y's. One with the positive version and one with the negative version. Okay, so that plus or minus is like a sign that most likely you don't have a function. And for example, here, if we try to solve for y, what happens? We get 9 minus x squared, that's y squared. But then I want to solve for y, so I need to take square root, and then we obtain this. In other words, here we get two expressions, right? So we get that y equals square root of 9 minus x squared, but it could also be negative square root of 9 minus x squared. So this is telling me that with the exception of 0, for example, or 9, right? If you put 0 or 9 in here, actually, no. With the exception of 9 or negative 9, 3 or negative 3. So if you put 3 or negative 3 in x, then you're going to get 0 here. So you get only one y, okay? But with the exception of those two numbers, any other x that you put that's valid, like for example 0, you're going to get a positive version and a negative version. So each x will have two y's, with the exception of those two that I said. Just remember in the circle there are these 2 points here that you only have, you have a tangent line, you don't have a secant line, so there's only 1 point really. So that x only has one y in the circle. But other than that, when you look inside the circle, then every x has two different y's, one positive, one negative. In fact, what's happening here is a circle is made out of two functions, okay? For example, this circle is made out of this function, and that goes from negative 3 to 3 and 3, and then the bottom function. So this one right here is a function negative square root of 9 minus x squared, and this one up here is a function square root of 9 minus x squared. So the red, if you look at the red piece only, that's a function. If you look at the blue piece only, that's a function. You put them together, you get your circle. Okay, a circle is a combination of these two functions. It turns out that circle itself is not good as a function. Anyways, the point is that when you solve for y, and if you get this sort of behavior, as I said, you already know that you don't have a function. Okay, it's no longer a function. So this tells me that y is not a function of x. And typically this is the way we say it, because you may be thinking about, is x a function of y? But typically when you see x and y, we think of y as being, is it a function of x? In other words, x stands for the domain and y stands for the range. Okay? Unless you're total otherwise. So in this case, y is not a function of x because each x has two different y's. And now you can use a formula to find your counterexample. Since, let's say, when x is 0, then y is going to be plus or minus 3. So 0 is related to either positive or negative 3, so it's not good. Okay, any questions? All right, so let me give you some examples. Another example, let's see, do y squared plus 2x equals 5 minus 3x squared, and do 2x squared minus 5y equals 3x plus 2. So what I want you to do is to determine whether, the curve, the relation, whether the relation defined by these equations is a function or not. That's what you need to do. By the way, notice that now in this language that we have introduced, if I ask you for the domain of number 1, what is it that I'm really asking you? I mean, that's a relation, regardless whether it's a function or not. Therefore, it has a domain. To ask you, find the domain, what is it that I'm asking you? What does it mean to find the domain of an equation? Yes?
It's the function of the x.
In other words, what am I asking you? To solve the equation. So a fancy way of me telling you solve this equation is to ask you find the domain. Okay? But remember, math is a language, so there are many ways that you can say the same idea. Okay? Solving this equation is equivalent to asking for the domain of this relation. Okay. Solving for x. It's just that here, this is to solve the equation, you need both x and y. I guess I have to ask you for both x, domain and range because you need to give me other pairs. Okay. Anyways, how about number 1? Is it a function or not? Why?
It becomes plus or minus when you take the square root of both sides.
Very good. So again, you solve for y, right? Remember here, really the question is y is a function of x. That's really what we're trying to figure out. Okay. So maybe I should write it down. Specify. So determine if y is a function of x. So to do that, just try to solve for y. Okay. So in number one, we can solve for y. Just move the 2x to the other side. So you get 5 minus 3x squared minus 2x. Then we take square root. But remember, every time that you take square root, you need to write plus or minus. Okay, so this right here is a sign that is not going to be a function. Now, you need to give me a counter example, something concrete. Okay? For instance, this allows you to find such a counter example. So can you give me a counter example? So if you say it's not a function, that means you need to give me an x that has two different y's. Okay, that's what you need to give. So can you tell me something here?
X equals 0 is y plus or minus y.
Exactly. So when x is 0, so it's not a function because, for example, when x is 0, we have y is either positive square root of 5 or negative square root of 5. You put 0 here and then you get those two, right? So not a function. Not a function. And then we can say, well, since 0, or I just, let me be a little more precise. So not a function since the point 0 comma square root of 5 and 0 comma negative square root of 5 are on the relation. Right? So 0 is related to both square root of 5 and negative square root of 5. So this is another way of saying that this is a solution to that equation. This is also a solution to this equation. Okay? Very good. Questions about number 2? Is y a function of x? Yes or no? Yes, it is. Good. So here we solve for y. What do we get? Let's see. This guy out actually. Oh, okay. Super lag. Okay, so I'm gonna bring the x's over here, bring the y over here, and then divide by 5. So we get y equals 2x squared minus 3x minus 2 over 5. So notice that here the plus or minus didn't appear, and we managed to have a formula. So y equals some expression that only has x's in it, and there's no plus or minus. So this means that for each x that you give me, whatever x you want, as long as it is okay, and in other words, as long as it is in the domain. So for each x in the domain, you put it here, you evaluate, you're gonna get only one number as a result. So one y corresponding to. You understand this? The difference between this and this one. Here for each x, you're gonna get two guys. One positive, one negative. Yes?
So if it has y to the square, it's not gonna be a function. If it's just y, it's not gonna be a function.
And not necessarily. I'll give you an example right now. So, yes, it is a function. Now, of course, when I said not necessarily, it's because there is an example in which that happened and it's still a function. It's just that you can think of it as a little stupid example, but it's an example. I mean, it's there, so you cannot generalize like that. So let me give you the example. Let's see, what is this? What's the graph of this?
No, it can't be a circle because it has no radius.
This is a relation. Because every equation defines a relation, okay? And then its graph is, when you look at all the points that defined on this relation and you graph them. So what is it?
Plus or minus x.
Plus or minus the square root.
Correct.
No, square root of x squared.
It's a circle with a radius of 0.
What is that?
There's nothing on the point.
What point? What point?
0, 0.
Very good. This is a fancy way of talking about the origin. Okay? The graph of this is just a point. There is only one point to find this equation, namely 0, 0. Do you understand this? So, I mean, it's silly, but it's, it's what it is. So, what's the graph of this guy? That's just a point. That's this guy right here. So, a circle with radius 0 is just a point. Okay? And of course, I could put here, I could also put x minus 3 plus y minus 7 equals 0. Then it's just this point moves somewhere else, right? 3, 7, for example. Okay? The point is that this is a point, so it's a function. Points are functions. Because when you do the vertical line test, what happens? It only goes at one point, right? So this is a function, but and the y shows up squared, okay? So this is a point, namely 0, 0, okay? So as a relation, so it is a function. Because, it satisfies the condition that each element in the domain has only one element in the range. In this case, it's only one guy, so 0 is only related to 0, and that's it. Do you understand this? So, I understand it's, it's a linear string, but I don't want to say that, every time you see a y squared, it's not a function. Well, it is the case. You see a y squared, and it's a function. Now, other than this, most likely it's not going to be a function, okay? So, all right. Questions? Actually, now I'm getting a little bit, I mean, it's part of this, but, I'm going a little bit to extremes, but it's good to think. So I want you to think a little bit about this. We're not talking about real numbers here. Is this a function?
You said we're only talking about real numbers?
Yes. So let's see, we managed to understand number 3 because we thought about it as a graph, right? We realized this was a point, and points are good. How about this one? Yes? Okay, so what does that mean? So what's the solution to this? For example, the solution to this was 0, 6, right? What's the solution to this? There is no solution. So what does that mean? There is no other pair that satisfies this. In other words, what is our relation? There is a relation here. It's the empty set. It's the set that has nothing in it. So question, is the empty set a function? Right? That's really the question that I'm asking here. So if a relation is a set. It's a set of ordered pairs, but it's a set, therefore, it could be that, it has no solution. Let me start writing stuff. So no solution. So if you think of this as a relation, this is just the empty set. So the question now is this a function? Is the empty set a function? Now here is the tricky thing. If you tell me that it's not a function, you need to justify. You need to tell me why. And to tell me why something is not a function, you need to give me an x that has 2 different y's. Can you do that for me? No, because there is no x to begin with, okay? So because you cannot tell me that it's not a function, then it has to be a function. The thing is that here things are binary, okay? You cannot have something that is, is neither one nor the other. It's either a function or it's not a function. There is no in between. Because you cannot justify that it's not a function, then it has to be a function. In math, this happens a lot. When this happens, this is like a vacuous statement, okay? It vacuously satisfies the condition. Why? Because you cannot tell me that it doesn't satisfy the condition, okay? So it's a little bit extreme, but it is a function. So.
Yeah, it does pass the vertical line test.
Eh?
No, that it passes the vertical line test.
Exactly. So you cannot draw a vertical line that crosses 2 points because there are no 2 points
There are no points.
to cross. Exactly. But you know, it's a little bit, it's different to what you are accustomed to see. So it is a function. Okay, because you cannot tell me otherwise. You cannot disprove this. So it must. Okay, but away from these extreme scenarios, yes, you see a y squared, then most likely it's not going to be a function. Okay, away from this extreme scenario. Okay, good. Any questions? So do you understand how to tell whether an equation represents a function or not? Okay, perfect. So now that we know that, then you know, let's talk a little bit more about functions. So let's talk about function notation. Okay, so let me make sure that I'm not missing any example to do. Actually, yes, you see, I was missing something. So let me copy and paste this. So this is just to practice a little bit more the vertical line test. So here there are two pictures. Let's tell whether these are functions or not. So this one, and then we have this one. And the rest is something else. There we go. So again, once the graph is given to you, it's pretty easy. That's why you're gonna see that we're gonna spend a lot of effort, you know, being able to graph functions. Because the point is that once you have the graph, you basically have everything that you want to know about the function is right there in front of you. So that would be the upshot. Given an equation, how do we graph it? Okay, how can we come up with this graph? That's why I was telling you, you know, you cannot use graphing calculators. Otherwise, what's the point of this course? If you have a graphing calculator, you have everything that you need. Okay, so how about this one? Is this a function?
No.
Why?
Because it doesn't touch the vertical line.
Exactly. If I draw a vertical line, it crosses at 2 points. So that's it, not a function. You okay with this? How about this one? Is this a function? Yes, it is. You know, if you look at it carefully, then hopefully you will agree that no matter what vertical line you draw, okay, this thing doesn't want to select itself. What's going on? I want blue. I will close you. Open you again. Windows. Okay, so I want blue. Okay, so no matter what vertical line you try to draw here, okay, I mean the graph is very high, but the point is that no matter what vertical line you draw, you will only cross at 1 point, okay? This, it may seem like a straight line, but this is not really a straight line. This is just that this is very steep, okay? So it has a very steep slope, but it's going up, but it's opening towards the right little by little, okay? It's a little bit slow the way it's going towards the right because it's super fast going up, but still it's going to the right and to the left over here. So no matter what line you draw, it will be, you know, it will only cross it at 1 point. So yes, it is a function. Do you understand this? So make sure that you don't draw horizontal lines. Horizontal line is for something else, okay? So when we talk about inverse functions, then you're gonna see the notion of one-to-one, and then we're gonna have horizontal line text to tell whether something is one-to-one or not. But for function is vertical line, okay?